This video is, remove my paper, for section 510. Example 1 in section 510. So 510 is an introduction to optimization problems, and 511 is just to continue with solving them. So optimization problems are similar to what they list here. You're finding things like greatest profit, least cost, least sized, greatest distance. So you're finding max and mins. We're going to go through this example, and then the next page we'll kind of go through the steps, but I'll also go through the steps here. So if you read this example, a manufacturer wants to design an open box, so no top, having a square base and a surface area of 108 square inches. What dimension should the box be in order to produce a box with maximum volume? So we are going to find the max, so like think relative max or absolute max of a function, and the function that we're going to need to find the max of will be volume. I put some notes already on here, and so you should probably, after I talk through these notes, pause the video and copy them. So what we're doing is we need to write a function to find volume. When we write this function, or before we take the derivative of this function, we want it to be in terms of a single variable. So these problems will always have something they give you and something you find. In general, what happens often is the function that you need to find the max or min of will have two different variables. The other information, or the given, is what you'll use to rewrite this function in terms of a single variable. So what they gave us was surface area. So surface area is the area of all the sides of this box. So it has 4 sides, and it has a top and a bottom, but the top is open. They've told you that these are both X. So the picture to me is a little misleading, but those dimensions are both X, and then this is the height. So if you think about the surface area, we have one end, which has an area of X squared, because it's square, and 4 sides, which have an area of H times X, or X times H. So the surface area will be the area of one end plus the area of 4 sides, and that equals 108. So that's what we know. This is what we're trying to find. What is the maximum volume of this box? So the volume is always length times width times height, but in this case, our length and width are the same. So the volume is X squared H. Now, we're going to want to take the derivative of this. We're basically finding the max of this function. Take the derivative, set it equal to 0, solve for our variable, verify it's a max, and then say, okay, that's the dimensions that will give me max volume. We need this to be a single variable, though. It's not like those related rates where we do implicit, because we don't have things moving. We don't have rates. So we want to rewrite this in terms of a single variable. The given function is what you'll use to write the function you need to take the derivative of in a single variable. So I want to write volume, so it is in terms of X only. So I'm going to take this surface area function and solve it for H. And then I'll replace this H with what I end up over here, so I'll have all X's. So I would minus X squared from both sides, and if you haven't paused the video and copied these notes, I would do that now. And then to get H by itself, divide both sides by 4X. So H equals 108 minus X squared over 4X. So I'm going to take this and replace it with the H here. So my volume will be X squared instead of times H times all of this. 108 minus X squared over 4X. Okay, I know I have to take the derivative of this and set it equal to 0, so I want to simplify that. this x would divide into there, so that would be 1x. If I distribute this x, I would have 108x minus x to the third over 4. If I divide that 4 into both parts here, I have 27x minus 1/4 x to the third. Okay, so this is my volume. Now I need to find the max of that function. I need to find what x value will give me the max of this volume. So just like in a normal function, we want to take the derivative of it, which would be 27 minus 3/4 x squared. Set that equal to 0, which would be x squared 3/4 x squared equals 27. Divide both sides by 3/4, and you're going to get x squared equals 36. So x equals plus or minus 6. X is a dimension, so we're going to ignore the negative dimension, and we're going to say x equals 6 is our critical point, and now we have to figure out, do we have a max or a min at 6? So you can do first derivative test, right? We could do a sign chart and do first derivative and check to see if we're increasing and then decreasing. I am actually noticing that I can take the derivative of this. So I'm going to do second derivative test. And then see if I'm concave up or concave down at x equals 6. So second derivative is going to be 0 minus 6/4 x, or negative 3 over 2x. And then I'm going to evaluate the second derivative at my critical point here at 6 and see if I end up with a positive or a negative. I already know I'm going to end up with a negative, and that is negative 9. So second derivative is negative or less than 0, which means my function is concave down, and I do indeed have a max at x equals 6. So I know x equals 6 is a max. Now, make sure you answer the question they asked. The question said, what dimension should the box be? So we know x equals 6 will give a max. We have to also find h. So our dimensions of our box are x and h. You have a very nice formula here already set up for h equals. So we're going to find h using that formula. So it will be 108 minus 6 squared over 4 times 6, which is 72 over 24, which is 3. So h equals 3. So my volume, remember, was x squared times h, or x times h. So the dimensions should be 6 inches by 6 inches by 3 inches. All right, that's your first optimization problem.